This episode examines where energy, greenhouse gas emissions, and climate hazards intersect with water engineering. It draws only on the authoritative evidence logged for this episode and frames engineering trade-offs and a practical decision framework for designers, operators, and planners. The material that follows preserves the research sources and the episode's analytical framing, while focusing on practical implications for project-level choices. Chapter 1. The Energy-Water Connection. Observed fact. The U.S. Environmental Protection Agency reports that drinking water and wastewater systems account for approximately 2% of U.S. energy use and produce more than 45 million tons of greenhouse gases annually. This figure is U.S.-specific and must not be generalized without additional regional analysis. Stated assumption. Energy demand in the water sector is primarily driven by mechanical processes, for example, pumping and aeration, and can therefore be influenced by technology choices and operational strategies. Illustrative example. Consider a municipal water utility where electricity powers pumps to move water uphill and blowers to supply oxygen in treatment basins. This is an illustrative scenario showing how a relatively small number of equipment classes commonly dominate a utility's energy footprint. The EPA guidance highlights these energy-intensive processes as primary targets for efficiency improvements, without prescribing a single technical solution for every system. Recommendation. Treat water systems as integrated energy systems. Begin with an inventory that identifies where electricity and fuels are consumed, then quantify emissions associated with those energy uses. Use that inventory to prioritize measures targeted at the most energy-intensive processes. Align operational changes and capital investments to the quantified opportunities identified by the inventory, rather than assuming blanket upgrades. Chapter 2. Where pumping and treatment consume energy. Observed fact. The EPA identifies pumping and aeration, including treatment operations, as among the most energy-intensive components of drinking water and wastewater systems. Stated assumption. Reductions in energy use for pumping and treatment are achievable through a combination of equipment upgrades, operational control, and system-level demand management, although the magnitude of savings is asset and context-specific. Illustrative example. An operator who staggers pump runtimes to avoid simultaneous starts or adjusts blower speeds in response to real-time dissolved oxygen measurements illustrates operational approaches that can reduce energy use. These tactics reduce peak electrical demand and allow equipment to run closer to their most efficient operating points. They are consistent with the kinds of efficiency measures the EPA recommends and are often among the lowest cost first steps after a targeted energy inventory. Recommendation. Prioritize an energy audit that maps pumping and treatment energy use component by component. Evaluate low-cost operational changes first, control logic, sequencing, and set point optimization. Then consider capital upgrades where lifecycle analysis shows net benefit. Sequence interventions to limit the risk of oversized or misdirected investments. Assess, optimize operations, then invest. This reduces the chance of retrofitting equipment that could have been made more efficient through controls and scheduling alone. Chapter 3. Carbon Accounting Boundaries. Observed fact. The sources in this episode provide sectoral and policy context, but do not supply a globally comparable life cycle carbon baseline for all water assets. The EPA gives U.S. sector figures, while UNESCO and the World Bank address policy and resilience rather than a single carbon accounting protocol. Stated assumption. Meaningful carbon accounting for water infrastructure requires explicit boundaries. Direct emissions from on-site fuel use, indirect emissions from purchased electricity, and embodied carbon in materials and construction. The research log indicates that this level of disaggregation is necessary, but is not supplied as a single standard across the sources. Illustrative accounting exercise distinguishes on-site diesel generator emissions, which are direct, grid electricity for pumps, which is indirect, and emissions embodied in concrete and steel for a new treatment plant, which are embodied. Making these distinctions is essential when comparing options such as electrification versus on-site combustion, because outcomes depend on grid carbon intensity,
fuel types, and the embodied emissions associated with construction materials. Recommendation: define project-level carbon boundaries before comparing alternatives. At minimum, separate direct on-site emissions, indirect electricity emissions, and embodied materials emissions. If possible, include life cycle stages over the asset's operating life. A consistent boundary enables clear comparisons across candidate measures and prevents hiding emissions in upstream material production or in electricity supply. Asset and region-specific baselines are required for robust choices. Chapter 4: Climate hazards across asset life. Observed fact: the World Bank Design Brief recommends explicitly incorporating climate resilience into water and sanitation engineering by addressing hazards including drought, floods, and high winds from storms over an infrastructure component's operational lifetime. UNESCO's World Water Development Report 2020 emphasizes that climate change affects societies mainly through water, altering availability, quality, and quantity, and creating risks for energy production that in turn affect water services. Stated assumption: infrastructure designed without projecting the range of future hydrological and meteorological variability is more likely to require adaptation or early replacement within its intended service life. Illustrative example: consider a treatment plant sited without accounting for increasing storm intensity. Flood inundation could disrupt power and treatment processes, requiring emergency bypasses or temporary treatment measures. This example shows how a failure to screen for hazard escalation translates into higher operational risk, repair costs, and potential service interruptions. It also illustrates the World Bank recommendation to plan across hazard types and life expectancy. Recommendation: incorporate multi-hazard climate screening into preliminary design and asset management. Screen for drought, flood, wind, and cascading energy risks over the expected operating life of each component. Then translate hazards into concrete design criteria and operational contingencies using resilience guidance and comparable planning tools. Document the assumptions that underlie hazard scenarios so future reviews can reapply updated climate information. This reduces the risk of reactive, costly retrofits and supports durable service delivery. Chapter 5: Adaptation and Mitigation Trade-offs. Observed fact: UNESCO frames water management as relevant to both adaptation and mitigation. Water measures can reduce climate vulnerability while also influencing greenhouse gas emissions through energy use and management choices. Stated assumption: actions that increase resilience are not always net low in emissions. Conversely, decarbonization measures can create resilience benefits or costs. Trade-offs must be evaluated contextually. Illustrative example: installing redundant diesel backup generators improves resilience to grid outages during storms, but increases direct fuel emissions when operated. Alternatively, on-site batteries charged by intermittent renewable electricity reduce fuel emissions, yet may increase upfront embodied carbon and require attention to supply security and life cycle replacement. Which option is preferable depends on local grid carbon intensity, hazard profiles, operational priorities, and procurement practices. This example illustrates the trade-off space rather than prescribing policy. Recommendation: conduct integrated appraisal that compares resilience gains and emissions impacts across candidate measures. Use scenario analysis to compare outcomes under varied climate hazards and energy pathways rather than optimizing for a single metric. When trade-offs are identified, make explicit the valuation of resilience versus emissions outcomes so choices are transparent and defensible. Comparing multiple features and multiple indicators helps reveal solutions that perform well across a range of plausible conditions.
Observed fact: the World Bank recommends that resilient design account for hazards over the operational life of assets and focus on engineering solutions robust to droughts, floods, and storm winds. Stated assumption: resilience is achieved through a mix of design hardening, redundancy, operational flexibility, and governance arrangements. No single approach delivers universal resilience. Illustrative example: resilience measures can include elevating critical electrical equipment above flood levels, providing multiple independent power feeds or diversified energy sources, and designing treatment processes that can operate at reduced capacity during droughts. These examples show how structural measures,
combined with operational plans and governance mechanisms, increase the chance that systems continue to deliver services under stress. Recommendation: adopt a layered resilience strategy. Harden the most critical components, build redundancy where failure would be catastrophic, and embed operational flexibility so systems can degrade gracefully under stress. Translate hazard screening into prioritized, costed interventions and update asset management plans. Maintain clear governance roles for emergency operation and plan exercises that test responses to simulated failures. This aligns with World Bank guidance to integrate design, operation, and governance for durable water services. Chapter 7: Financing and Prioritization. Observed fact: the research log highlights the absence of a single global financing prescription. Priorities depend on asset and region-specific baselines and quantified adaptation benefits, which are not provided in the cited sources. The World Bank brief and UNESCO report imply that financing decisions should be guided by quantified risk reduction and life cycle analysis, but the episode sources do not prescribe funding mechanisms. Stated assumption: priority investments should be those that deliver the largest combined benefit in resilience and emissions reduction per unit cost when measured over an appropriate life cycle horizon. Illustrative example: an illustrative prioritization might compare replacing inefficient pumps with relatively low capital cost and high energy savings potential against constructing a new flood barrier for a treatment plant with high capital cost and a large resilience benefit. Decision makers need quantified benefits, local cost data, and financing constraints to determine the preferred sequence. This example is not drawn from a specific case study. Recommendation: use a cost-benefit or cost-effectiveness framework that monetizes or otherwise scores resilience benefits and emissions reductions over asset life. Prioritize measures with high benefit-to-cost ratios and favorable life cycle emissions outcomes. Where data are lacking, fund pilots to generate baselines and operational performance information before scaling costly interventions. Tie financing decisions to the outcomes defined in the appraisal, so investments reflect declared priorities and can be evaluated against measurable targets. Chapter 8: A decision checklist for low-carbon resilience. Observed fact: the cited guidance collectively supports structured assessment, inventory energy and emissions, frame water measures as both adaptation and mitigation, and incorporate multi-hazard resilience across asset life. Stated assumption: decision makers benefit from a repeatable checklist that integrates energy, emissions, and hazard screening into programmatic planning. Illustrative example: the following checklist is illustrative and intended as a practical framework to be populated with local data and specific criteria. Recommendation: implementation and decision framework checklist. First, define boundaries and objectives. Set carbon accounting boundaries for direct, indirect, and embodied emissions, and define resilience objectives, time horizons, service levels, and acceptable risk thresholds.
Second, measure current energy use by component, including pumps, aeration, and pretreatment, and record recent hazard exposures and failure modes. Build an emissions baseline consistent with chosen boundaries. Third, screen hazards over asset life. Evaluate drought, flood, wind, and cascading energy risks for the planning horizon, and document plausible severity and frequency scenarios. Fourth, identify candidate measures. Propose operational, equipment, resilience, and low-carbon energy options, and describe expected performance, costs, and interactions. Fifth, screen for trade-offs by running scenario analysis, comparing emissions and resilience outcomes under plausible futures. Where trade-offs exist, document the decision rationale. Sixth, perform life cycle costing and emissions assessment. Rank interventions by benefit to cost and co-benefit metrics, and consider affordability and financing constraints. Seventh, pilot, monitor, and iterate where uncertainty is high. Collect operational and emissions performance data to refine models and update the business case before large capital outlays. Eighth, align governance and financing with prioritized outcomes, including resilience and emissions metrics. Ensure clear roles for procurement, operation, and oversight. Concluding voice:
Observed fact. The evidence for this episode establishes 3 pillars. The water sector is energy-intensive in key processes. Water is the principal medium through which climate impacts are felt, linking adaptation and mitigation. And resilient engineering must explicitly address hazards across asset life. These pillars are supported by the U.S. Environmental Protection Agency, UNESCO, and the World Bank. Stated assumption. Effective water engineering in the era of climate change requires integrated energy and resilience planning, anchored in site-specific baselines. Recommendation. Use the decision checklist as a starting framework. Measure, screen, compare, pilot, and scale. Where the cited sources leave open questions, such as precise life cycle carbon baselines, prioritize data collection and targeted pilots that close those gaps before large capital commitments. Apply transparent assumptions, document scenario choices, and update plans as new data become available. This disciplined, evidence-led approach helps preserve service reliability, reduces emissions where feasible, and adapts systems to climate-mediated water risks, underscored by UNESCO and the World Bank.